Okay, so let's begin. Um, if you have any problem in between, you can always unmute and raise up the question because I cannot see you guys on the Teams window. Okay, so welcome. I welcome all of you to this tutorial session or the TA session for the NPTEL course Principles of Signals and Systems offered by Professor Aditya Jagannathan from IIT Kanpur. And this is the first TA session for this course. And my name is Yashvanth. I am presently a PMRF PhD student at the Department of EC at Indian Institute of Science, Bangalore. And I also come under the so-called fellowship PMRF, which stands for Prime Minister's Research Fellowship, which is one of the prestigious fellowships in the country for PhD students. So, I'll be basically doing these TA sessions as part of the PMRF deliverables. So, and I'm currently advised by Professor Chandra Murthy from the EC department at IISc Bangalore. And my research interests broadly lie in signal processing and applications of signal processing in wireless communication systems. Okay, and my research focus is on something a novel technology called intelligent reflecting surfaces for 5G and beyond wireless com. If you have any queries concerning, in general, some basic doubts on the domain, or in particular of the contents that I'm going to cover in the tutorials, you're welcome to write to the email yashvanth@isc.ac.in. And I also have a small web page where you can find more details about me, and that's also given here. Okay, without further ado, let's get started. So the topics that are going to be covered for week one are just to get started with basics of signals, classification of signals, that is, what are the various types of signals, and some introduction to systems. Okay. Just to confirm, can you all hear me? Is it okay until now?
Yes, sir, you are audible.
Okay, thanks a lot. Okay, so the way I have structured, and I will be I've structured all the tutorials or the TA sessions and will follow throughout this semester. Is that all the TA sessions will be categorized into two parts. The first part will be basically walking through the summary of all the lectures um, that were covered by Professor in that particular week. For instance, in today's session, I will walk through a quick summary of everything that has been done in this week. That is first part. The second part will be on tutorials, wherein we will look at some problems, example problems, and some of the interesting problems based on the contents that were taught in the class, which will be helpful for you to solve all your assignment problems. Okay, and also learn about the course little more extra in general. Okay, so there's going to be two part. Roughly the part one can take anywhere between 25 to 35 minutes. Part two will be the rest of 1.5 hours, where we will look at some problems and then we'll solve them in life. Okay, so these are the two parts. So let's get started with the first part, which is the summary part of lectures of week one. Okay, so the lecture started with the notion of signal. Okay, so then what is a signal? Right, that's the fundamental question to this course. A signal is basically a function that conveys information about some phenomenon. Okay, you can think, for example, if you go back to mathematics, you would have learned, all of you know what a function is from your high school, right? So if I say that there is a function, we generally used to denote f of x as a function. Now consider that x is playing the role of t, a dummy variable t, and let's say your f is like x, so it's like x of t. It is essentially a function in t. So in particular, in the context of an electrical engineering background, a and signal, we call such a function as a signal. Okay, but that function should be something meaningful to us. We are engineers and we are more interested in something of practical use. So we want to only measure those functions which convey some useful information about everyday day-to-day things. Okay, so essentially, in that sense, let's say your x of t is a signal. Uh, can you all hear me well? Hello?
Yes, sir. Yes, sir.
Okay, you can hear me, right? So, in case you're not able to hear me or something happened, please let me know. Okay, you can just unmute and just tell me. Okay, so x of t is a
Okay, okay.
signal. Okay, so the input is basically set of all real numbers, and the output is, let's say, the domain of the domain is set of all real numbers, and the range of the function is -1 to 1. So then we use when then this is said to be a signal that takes all input variables as real numbers and outputs a number -1 to 1. In general, input is a time domain axis. That is, let's say, if I say x of t is equal to sine t, where t ranges from -infinity to infinity, that time essentially what I'm saying is at time t is equal to 2 seconds, what is the signal output? X of t is what? Basically x of 2, that is sine 2. Okay. So essentially the variable is basically a time. Generally, at least for the introductory signals and systems course, it is a time domain that is called as the that is the variable of your signal. Okay, it need not be time. For example, it could be spatial domain. That's so this is called a one-dimensional signal because it only depends on one variable. In general, it could be multi-dimensional. For example, your x, the signal could depend on t comma x. Sorry, maybe I will use some other letter s, where t stands for time and s stands for distance. Right. So it could be a function of both space and time. Okay, so there are multiple. This is called a 2D signal because it depends on two dimensions. One is time dimension, other is spatial dimension. Now, there can be multiple ways to define a signal, but this is the first course on signal systems, so it is better to just stick with one dimension, which is what we will be doing in this entire course. Okay, so x of t is basically your signal, which is depends on one variable t. Okay, so for example, what can this denote? For example, if you want to measure the temperature of a city, and let's say in some city you know that the temperature varies sinusoidally with time, then this x of t is equal to sine t to measure the signal that conveys the information about the temperature of a city. Okay, so that is one example. Now, typically we encounter signals that exhibits variation in time and space, but as I told, in this course we will only look at variations along the time domain, not in the space domain. Okay. Next, this is basically a very quick introduction of what a signal is. A signal is essentially a mathematical function that conveys information about some useful quantity that we encounter in day-to-day life. That's all. It's a function, mathematical function. Now, what are the different types of signals? That is the next part. So the first classification of a signal is what is called continuous time signal. What do you mean by continuous time signal? The continuous time signal, the argument that is a variable time is continuous in nature. For example, x of t is equal to sine 2 pi f t. Here, t takes any real number value. It could be any real number. Okay, that means it takes continuum values on the entire time domain. Okay, that's why it is called a continuous time signal. This is called a continuous time signal. Example is x of t is equal to sine 2 pi f t. Now, the second type of signal is called a discrete time signal. What is a discrete time signal? If you know what is a continuous time signal, discrete time signal should be clear. That is, in discrete time signal, the signal is measured only at discrete points in time. For example, what I'm saying is, okay, I will not say I will measure the signal at t is equal to 0, then t is equal to 0.5. No, I will not do that. I will only measure the signals at discrete time. For example, at t is equal to 0, at t equal to 1, at t equal to 2, at t equal to 3, and so on. Only at specific time instances I will measure the signal values. Those types of signals are called discrete time signals. Okay. So this is what is called a discrete time signal, where the time domain is essentially discretized. Okay, and typically it is you can think of this as essentially a sequence of numbers, because essentially what you have is at x equal to 0 you have one value x of 0, at t equal to 1 you have x of 1, at t equal to 2 you have x of 2, and so on. So it's basically a sequence of number x0, x1, x2, x3, and so on. So a discrete time signal is in some sense a collection of or the sequence of just the numbers, and these numbers are obtained at some discrete intervals of time. Okay. Now, you can always obtain a signal by sampling what is called a continuous time signal. That is, if I go back to a continuous time signal, as I showed in this picture, what I do is you take a t equal to 0, whatever is the value of sine, and t equal to 1, whatever is the value, equal to whatever the equal to 3, whatever is the value, and so on at different time, discrete time intervals. If you just sample the values taken by the sine signal, that will essentially give these sequence of numbers. So you can always obtain a discrete time signal by sampling a continuous time signal. Okay, so that is the relation between, though this is what I have told you. If you have a continuous, this green envelope, a continuous time signal, what you do, you take discrete time intervals on x-axis, that is a t-axis, and then you take the corresponding y-axis value, that is x of t axis values. And these numbers are basically discrete time. These are the numbers which form the discrete time signals representation. Okay, sampling any continuous time signal gives a discrete time signal. Okay, next classification is called an analog signal. An analog signal is basically that signal that takes values in continuous amplitude domain. Now, until now, we saw two types. One is continuous time signal and discrete time signal, where the classification was with respect to time axis. That is, either the time was continuous or time was discrete. Now, how about the y-axis? Suppose that is x of t axis. If I make the value on the x of t axis as continuous, then it is called an analog signal. Similarly, if I make values of the x of t discrete in nature, it's called digital signal. Okay. Now, analog signals are basically those signals that take values in continuous amplitude domain. Amplitude means essentially the y-axis value. And what are digital signals? Digital signals are those signals that can take values in discrete amplitude domain. That is, you cannot take any value on y-axis. You can only take some finitely number of values on the y-axis. That is called a digital signal. Okay. So, for example, if you take x of t as something like this, right? You take t and x of t, and it's a ramp. This is called a ramp. Okay, that is, it's like a slope, right? It's like a ramp that we see in everyday life. So this is also called a ramp signal. Okay, so it's a straight line. So x of t is equal to t. That is basically this function or this signal. Now you see here, for any t, if you take a particular value of t, the particular value of y is this. So the signal can take any continuous value between 0 and 1. Okay, when t is between some fixed interval here, right? This means this is basically a continuously varying amplitude. So this is an example for an analog signal, the continuous amplitude. So it's called an analog signal. However, if I discretize the same signal on the y-axis domain, it is called a digital signal. For example, you see here between in this interval of time, right? You only have y-axis equal to 0. Now, similarly, in this interval of time, you have y-axis equal to 0.3. And in this interval of time, you have 0.6. In this interval of time, you have y-axis equal to 0.9. Right? So it doesn't take, for example, 0.2. It doesn't take any number except 0, 0.3, 0.6, and 0.9. So such type of signals are basically discrete in amplitude, and so they are called digital signals. So until now, we saw four types of signals. One is basically a continuous time domain signal, then discrete time domain signal, then continuous amplitude domain signal, which is an analog signal, and discrete amplitude signal, which is a digital signal. These are the four types of signals we have seen. Okay, are there any doubts?
No, sir.
Okay. Okay. Now let us go to real signal. Okay. What is the real signal? Now we saw the x of t, the output, the function value, right? The range of the signal is a real valued function. If the signal is real valued, that is, the amplitude takes only real numbers, then such type of signals are called real signals. Example is x of t is equal to sine 2 pi of t. We know that sine 2 pi of t takes any number between -1 to 1 and +1. It cannot take any other number other than numbers within this range. So, and all numbers between -1 and +1 are real values. So sine 2 pi ft is an example for a real signal. Now, what is a complex signal? It's easy to understand. The signals that takes values belong to set of complex numbers. Example, x of t is equal to e power j 2 pi fct. Okay, this is the form e power jx, right? F of x is equal to e power jx. That is basically this form. This is looking like that form. So now this is a complex number. So for any t, the for any input t, the output is a complex number. So this is a complex valued signal. So for example, you can this by Euler's formula. This is nothing but cos 2 pi fct plus j sine 2 pi fct. So you see, it's a complex number. So the amplitude of the signal is the complex number now. So that's why this basically is called a complex signal. That is the next classification, deterministic signal versus random signals. So what is a deterministic signal? A signal whose value can be exactly specified at any time instant. Okay, example, if I specify t, right? If I give a particular value of t, then the output x of t should be fixed for at a when you at for basically should be fixed for any other spatial dimension, right? Then such type of signals are called deterministic signal. On the other hand, at any time instant, if the signal can take any value, then it is an example for a random signal. So to help you understand what is this, suppose let's consider the following example, right? I'm interested in measuring the temperature of a particular city X at 10 a.m. on every day. Okay, so I fix my T to be equal to 10 a.m. Okay, now if I measure the temperature today at 10 a.m., let's say I get uh, 5 degrees. Let's say I measure the temperature of the same city at same time 10 a.m. But tomorrow, then I need not get 5 degrees. I may get, let's say, 7 degrees. So although you basically tap the signal value at the same time, but when you measure for different time instances, you will get different values. The amplitude will keep changing, right? With time, that is at a given time instant itself, your function value need not be unique. It can take any value depending on some nature, law of nature. So here temperature is something that is not under our control. It's what nature gives us, right? So it's a random signal. So for people who know about probability theory, they'll be able to understand. Suppose you toss a coin or roll a die, you don't know what the output will be, right? So you can get either in the case of the coin, you can get a head or a tail, or similarly, in the case of a die, you can get any number between 1 and 6. But a priori, unless you roll the die, you will not know which number you're going to get. It's same thing is happening here also, right? You don't know the temperature that you will get on every day. Even if you fix the time, let's say 10 a.m. on every day, the temperature can still be varying with different days, right? So that is an example for a random signal. On the other hand, suppose if you are able to, if there is some artificial system where the temperature will remain constant, equal to 5 degrees at 10 a.m. on every day, then that is no longer random. That's a deterministic signal. That is, you can take any value at a given time instant. That is a random value. But if it's only a fixed value, right? That is, if I'm able to specify, if someone gives you the time instant, you can uniquely specify what is the output value at the time instant. Then such type of signals are called deterministic signals. Okay. Now, even signal versus odd signal. Okay, this is very interesting and important also. In fact, even signals and odd signals will keep coming throughout the course again and again, especially when we go to the concept of transforms like Fourier transforms and etc. It's important that we understand even and odd signals very well. But it's quite easy concept. It's nothing complicated, very easy. But if you have doubts, please unmute and ask. Okay. Now what is an even signal? An even a signal is said to be even if x of t equals x of minus t. For example, x of t is equal to cos 2 pi fct. Now, what we know is that if I take x of minus t, what is this? Cos 2 pi fct of minus t, which is nothing but cos of minus 2 pi fct. Now, can anyone tell me what is this equal to? Yes, someone just Unmute and tell.
Cos 2 pi ct होगा minus
FCT. That's all. This is a minus theta equal to cos theta.
yes.
So just I applied that. So this is nothing but x of t. So we started with x of minus t, and then we showed that is equal to x of t. So that means this function, this signal cos 2 pi fct is an even signal. That's because it satisfies the property x of t is equal to x of minus t. Okay. Geometrically, what it means is the signal. It basically if you take the positive axis on time domain, that is a mirror image of the signal on the negative time domain. Okay? If the signals are basically are symmetrical about your y-axis, this is your y-axis, right? If the signal is symmetrical about y-axis, then such signals are basically going to be even signals. That is t equal to 0 axis. This is a y-axis. If the signal is symmetrical, then it is an even signal. Now you might have guessed what is odd. It's exactly the reverse. That is, if you take x, if your x of minus t is equal to minus x of t, that is basically this is same as x of minus t is equal to minus x of t. That signal is a odd signal. Example is sine 2 pi fct. Why? Because if you take x of minus t is nothing but sine 2 pi fc of minus t, which is nothing but sine minus 2 pi fct, which is same as minus sine 2 pi fct, which is same as minus x of t. Correct? So essentially, these kind of signals are anti-symmetrical about y-axis. That is, if I take the mirror image of your positive y-t-axis, the mirror image will be exactly flipped version of the actual signal in the positive t-axis. Okay, it is not going to be symmetrical, but it is anti-symmetrical about your y-axis. These type of signals are called odd signals. Okay, next, periodic signal. So you might have now guessed what is a periodic means. A function is said to be periodic. What is basically property? F of x plus some x naught equal to f of x, where x naught is some fixed number, right? Then we know that it's a periodic signal, periodic function. Same thing for a signal also. If you can find some fixed number capital T, if there exists a capital T, fixed capital T, such that the x of t plus capital T equal to x of t, then this function x of t is said to be a periodic function, a periodic signal. Okay, if a function is periodic, then the natural question is what is the period of the signal? That is, after how many cycles will it repeat itself again, right? So for in this example, x naught is a period. Similarly, in this definition, t is a period. Okay, so x of t is a periodic signal if x of t plus capital T is equal to x of t, and it is periodic with period equal to capital T. Okay, example, if you take sine 2 pi ft, then we know that sine function is a periodic function. So then basically, if you can show that this is periodic with period equal to 1 by f. Okay, this is called the time period of the signal. So f is the frequency of the signal x of t. Okay, and that means what I'm saying is the capital T is the time after which the signal will repeat itself. That is called the time period. And for signal x of t is equal to sine 2 pi ft, the time period is equal to reciprocal of f, which is called the frequency of the signal x of t. Okay. So just an example, if you take sine 2 pi ft and let's say call it x of t, and you evaluate x of t plus capital T, that is same as sine 2 pi f of t plus capital T. Now use distributive law of multiplication. This becomes sine 2 pi f small t plus sine 2 pi f capital T, but I know that capital T is equal to 1 by f, right? So this f and capital T will get cancelled. So I get sine of 2 pi plus 2 pi f small t. But I know that sine of 2 pi plus theta is equal to sine theta. So this 2 pi, you would remove it. So it becomes sine 2 pi f t, which is same as x of t. Therefore, your x of t plus capital T is equal to x of t, which proves that sine 2 pi f t is indeed a periodic signal. And what is the period? Period is equal to capital T equal to 1 by f. Now, the corresponding analogy is aperiodic signal, means whichever signal is not periodic, that is, you can cannot express x of t plus capital T is, you cannot, it's not equal to x of t for any capital T. You, no matter what capital T you give, this equality will not hold. It will never be equal. Those kinds of signals are called aperiodic. That is, those signals which are not periodic are called aperiodic signals. Next important concept is called the energy of a signal. Okay, now energy is defined as follows. So if I give any signal x of t, the energy of the signal is denoted by E subscript x of t, is defined as, you see this new symbol, I put a triangle and a two and I underscore them. So this is a symbol in mathematics. This symbol is called defined as. Okay, so the energy of a signal is defined as integral minus infinity to plus infinity mod of x of t square dt. Okay, so this is for a continuous time valued signal. Now you see this, the integral is defined only if t is continuous. If it's a discrete time signal, how can you define integral? That's why people also came up with the definition of energy of a discrete time signal, which is defined as, so here t takes a value n, because I told that t is only over discrete points. So in general, people use n as the index for the signal for discrete time. That is, they measure n in terms of integers, 1, 2, or plus my, okay, maybe in general n can area 0, plus minus 1, plus minus 2, plus minus 3, and so on, because essentially the discrete time, I'm only measuring the signal values at discrete integral points of time, and so I'm calling n as the index instead of small t. Okay, now for a discrete time signal, the energy is given by sum over minus infinity to plus infinity mod of xn square. It's very similar to continuous, except that the integral is now replaced by summation. Okay, next is basically power of a signal. What is the power of a signal? The power of a signal is defined as, for any signal x of t, the power is given by limit denoted by px of t, given by limit t tends to infinity 1 by capital T integral minus t by 2 to plus t by 2 mod x of t square dt. That is, the difference is in the energy, what you had, you just had integral minus infinity to plus infinity. But in power, you just have over a finite range minus t by 2 to plus t by 2, and you take average. That is, you divide by the interval length, and then you take the t to infinity. That is the main difference. Why? This is because we know that power is equal to energy over time. What you do, so you calculate the energy over a finite range, and then you divide by the time over which you have calculated the energy, and then take over all time. Okay, this is basically, this definition is inspired based on this definition, that is, power is equal to energy by time. Similarly, if you have a discrete time signal, then essentially your power is given by, you take sum over a finite range of values x of n square, that is from minus capital N to plus capital N, and divide by the time of this range of this x of n, that is, there are 2n plus 1 samples in the summation. So divide by that and then take n to infinity. Okay, now some very important signals. First is called the unit step signal. Okay, unit step signal is one where for t greater than 0 it takes a value 1, and for t less than 0 it takes a value 0. Something like this is a graphical representation. U of t, for t negative t it is 0, and for positive t equals 1. Unit impulse function. So it's a very special kind of function. It's defined as limit e tends to 0 of some other signal called delta e of t, where delta e of t is basically this rectangle function. That is, from minus e by 2 to plus e by 2, you will have an amplitude of 1 by e. Everywhere else it is 0. This is called delta e of t. And what you do, you take the e to 0. Right? Then what happens? This is basically a rectangle which shrinks when e goes to 0, but the amplitude will grow. Right? So in the limit e is going to 0, the width is almost 0, but the height is infinity. Because 1 by 0 is very, very large number. It tends to infinity. So delta of t, this is how delta of t looks like. At t equal to 0, you have very large value. Everywhere else, it is not. It doesn't have any value. Okay, so this is called a delta. It's called a unit impulse function or impulse signal. Now it's a property that area under delta impulse function is always equal to 1. That is, you integrate delta of t from all the way to minus infinity to infinity, it is always equal to 1. Another property is that if you have delta of t and integrate from a to b, this value will be equal to 1 only if this interval, the range a to b, contains 0. That's because delta of t has some non-zero value only at 0. Everywhere else it's 0. Right? Only if the integral range contains 0, will this integral equal to 1, else it will equal to 0. Similarly, another important property is if I integrate from minus infinity to plus infinity x of t into delta of t minus t naught, that is, you multiply x of t and delta of t minus t naught and integrate it throughout, then this is same as replacing x of t with t naught times delta of t minus t naught dt. The reason is because simple. Only at the argument of delta should go to 0. Only at that point you have a non-zero value. That means that t equal to t naught, delta will go to 0. Delta of 0 will become non-zero integer. That's why over the entire integral, only when t equal to t naught, this x of t will sustain. Otherwise, it will be multiplied by 0. That's why you have x of t naught, and since area and x of t naught is now a constant because it is no longer dependent on t, because at the given t naught it's a constant. Bring this out of the integral. Now what remains is minus infinity to plus infinity delta of t minus t naught dt, which is integral is equal to 1. That's why this is equal to x of t naught itself. This is very important and famous property called the shifting property of a impulse function. Now, another signal is called complex exponential. That is, if your x of t is something like this, a times e power j 2 pi f t, this is called a complex exponential function. Why is it called complex? Because you have a j. This is essentially nothing but a cos 2 pi f t plus j times sine 2 pi f t under the bracket. Okay, this is basically a complex exponential signal. What is the real exponential signal? It's just of the form x of t is equal to e power sigma t, where sigma is a real number. Okay, so essentially, if sigma is a number less than 0, that is a negative number, then e power sigma t will go to 0 with t. But if it's a positive number, it will grow as t increases. Next is very famous, all of us know. It's called a sinusoidal signal, which we know. A sinusoidal signal is something of the form x of t is equal to a cos omega naught t plus theta. So a is called the amplitude of the sinusoidal signal, omega naught is called the frequency in the angular frequency, and theta is called the phase of the signal x of t. And similarly, all these special signals I told for continuous time signals, you can define a notion of similar notion in discrete time also. So you can have discrete version of these signals also. Now, last part of the summary on introduction to systems. Now, what is a system? A system that is something that basically processes an input signal and gives an output signal. Okay. For example, you pass input x of t. It's some box that does some mathematical operation. We don't know, but the output will be y of t, which is called the output. Okay. An example is an audio player, right? So you feed in some cassette to it. The cassette is there, and the tape will contain all the data, and there's some inherent system that's inside it, and the output of the this audio player is that you hear the sound. So it converts the input, basically the digital data stored on the tape, to the output, which is the audio sound. So in between there is some system we don't know, some black box. Okay, so in general we can represent such kind of system mathematically as y of t is equal to some transfer function, that is some t of x of t, where this t operation is something that you can mathematically define depending on what the nature of the system is. Okay, this is what a system is. System is something that will take input of x of t, processes, and gives output y of t. Now there are different, like how signals were classified. You can classify systems also. First one is called the memoryless system. That is, the output of a system depends only on the current input. That is, if you have y of t, it's a function of only x of t, not x of t minus epsilon and t plus epsilon for epsilon positive. That is, it doesn't depend on the past input and future input. It will only depend on the present input. That such type of systems are called memoryless systems. Something called causal systems. See the spelling, it's a new word. It's not casual, it's causal. Causal. Okay, it's called a causal system. That is, the output depends only on the present and past inputs, not on future values. So it's slightly little more than memoryless. Memoryless needs only present input, but in causal system, you are okay to take inputs. The present output can depend on past input also, in addition to present input. Okay, output depends on both present and past, but certainly not of future. Okay, an example: if you define your system as something that takes x of t as the input and gives the output as this integral minus infinity to t x of tau d tau. So what essentially it does, it takes all values of x from minus infinity to the present input t and then basically adds it up. Integral is nothing but limit of sum. So it adds up every single x for every t between minus infinity to current time t, but not for t greater than, so for tau greater than t, it doesn't add it, right? So that means the output depends only on past inputs and the present input, but not on future. So this type of system, right, that takes input as x of t and output is integral minus infinity to t x of t d tau, is this system which implements this operation is a causal system. Okay. Now, on the other hand, if you had allowed your t to go till infinity, that means what does it mean? Your present output will depend on future input also, because the integral ranges to infinity. That means, for example, if I want to say compute y of 3, you have to do, this is nothing but some so many summations, and it will involve x of 5 also, x of 5, x of 6, and so on, right? That means your y of 3 is computed based on x of 5. X of 5 is the future input, but y of 3 is the present output, which means present output is depending on future inputs also. So this type of a system is called a non-causal system, and in general they are not realizable. That is because you cannot predict what is going to be future, right? So in general, non-causal systems are not realizable in practice. However, for theoretical purpose, people do study, but mostly in this course also, we will only stick to and understand the properties of causal systems. Okay, so that basically concludes the summary of the lectures from this week. If there are any questions or doubts, this is the right time to ask. Yes, are there any doubts?
No, sir.
Okay. I got a no from one person. How about others?
No, sir.
Okay. So I'm only getting no's, and since I'm not getting any doubts from anyone else, I assume everything is clear till now. So let's now go over the second part of the tutorial, the TA session, namely on some tutorials. That is, we'll solve some problems and solve based on the concepts which we discussed today. Okay. The first question, the problem that we're going to solve is as follows. Question is, show that
Hello, sir.
any, yes,
I'm audible, sir.
yeah, you're audible. Go ahead.
Actually, my question is not from a lecture video, but I have a doubt in delay and advance signals, shifting right
Hmm.
side and left side.
Okay. Fine. Hmm. What is the exact doubt? Let's see if it is within the if whatever your doubt is within the scope of today's class, we will answer. Otherwise, we will take it up certainly in future, because in future classes this will come. In fact, you have not yet seen the concept of time variant system and time invariant system. That will come in future classes. So, but you can anyways ask your question, and then we'll see whether it is within today's class or maybe we should take it in future. Let's see. What is the question?
Okay, sir. I have doubt regarding the difference between delay and advance. That's like in
Ah,
our college, it's going on delay and advance topic. So I thought I not got
okay.
any.
Okay, so not that's not very difficult. I'll give you a very high level example of what is a delay and advanced. So let's say x of t is your actual signal. Okay, then some y of t is equal to x of t minus t naught. This is said to be a delayed version of x of t. Is it okay? Why is this called x of
Yes,
x
sir.
of? Let's understand. Let us understand why this is called the delayed version. Okay, so let me maybe push this down a little bit. This is called a delayed version. Let's take an example. If I'm saying, let's say I'm interested in x of 5. Okay, but let's say t naught equal to let's say 3, right? When I actually want to see the value of x of 5, your y of t, that y of 5 is only x of 5 minus 3 equal to x of 2. I should have ideally read the value of x of 5, but I'm only reading the value of x of 2, which is the delayed version, delayed by a factor of 3. Okay, so a function, a signal x of t minus t naught for positive t naught, that is very important, only if it's positive, is said to be a delayed version of your x of t. The y of t is t naught units delayed by delayed version of the signal x of t. Okay. Similarly, if it's advanced, means y of t equal to x of t plus t naught for t naught being positive. This is nothing but an advanced version of x of t. Why? Hey, take an example. Let's say I actually want to read x of 5, but same t naught equal to 3. But I'm actually reading y of 5 equal to x of 5 plus 3 equal to x of 8. I should have read x of 5 now, but I'm reading x of 8. That is, I should take the output of the signal at t equal to 5. But the output, whatever is coming out, is not corresponding to t equal to 5. It is corresponding to t equal to 8, which is something future value. So that's called advanced version of x of t. So delayed version means it implicitly, if someone says x of t is delayed, that means they are referring to the signal x of t minus t naught for some positive t naught. Similarly, if someone is saying x of t is advanced, means they are referring to x of t plus t naught for some positive t naught. Is it clear?
Yes, sir. Thanks.
Yeah. Okay, now let's go to the questions. Uh, um, just a minute. Okay. Okay. The question is as follows: show that any signal x of t can be decomposed into an even signal and an odd signal. Okay, what do I, okay, this is the question. Now we'll see the answer. Now, what do, first I need to, let's understand the question. The question is saying, you need to show that any signal you take x of t, you can write it as, what do you mean by decomposed? Can anyone tell me? Can anyone tell what do you mean by decomposed?
To differentiate from
Sir, I
anything.
think we have to write the definition of even and odd signal here.
Okay, okay. So what it says is, let me explain. What it says is, you should be able to write any signal x of t as sum of two signals, y1 of t plus y2 of t, where y1 is an even signal and y2 is an odd signal. That's the meaning of this statement. That is, decomposed means sum. You can that is, any signal x of t can be written as sum of two signals, where sum of two signals, in the two signals, one signal should be even signal, other signal should be odd signal. That is the meaning of decomposition, right? Decomposition means what? Something, there is something and you want to decompose into two parts. That is called decomposition, right? So here you want to show that any signal can be decomposed, that is written as a sum of an even signal and an odd signal. That is the meaning of the question. So this is the question, and it's very useful property. Maybe you might not realize it in this this first week, but as you go in deep in the course, especially on Fourier transforms, and you understand different properties of Fourier transform, this is a very useful property you will use, because this property is true for any signal. So using this property, you can derive many more nice results, nice properties of Fourier transforms. Okay, but first you need to understand why this property is correct. That is the question. You show that any signal x of t can be decomposed into even signal and an odd signal. Okay, that's the requirement. Now let's do the answer. Let Px of t be any general signal. Okay. Now I can write x of t as x of t plus x of t by 2. Okay, I'm just writing, I'm just adding 2 times and then dividing by 2. This is same. There's nothing I'm doing, no magic I'm doing. Now what I will do is I will add and subtract x of minus t in RHS. What do I mean by that? Um, Basically x of t, I can write this as x of t plus x of t by 2 plus x of minus t minus x of minus t. Anyways, this is 0. There is this, so it doesn't change the value. Now I will what I'll further do is this is same as x of t plus x of t by 2 plus x of minus t minus x of minus t by 2. It doesn't matter if I divide 0 by 2. Anyways, it is 0. So I'm just dividing it by 2. Now I will rearrange. That is x of t equal to x of t plus x of minus t by 2 plus x of t minus x of minus t by 2. Is there any doubt in this step? I just took this x of minus t to here and I took this x of t to here. That's all. Nothing else I did. Is there any doubt?
No, sir.
Yeah. Now my claim is this is an even signal. This is an odd signal. That is my claim. I will prove that. Okay. Now claim is call this as y1 of t. Call this as y2 of t. Now this is claim is, I will write it separately. Claim y1 of t is even signal and y2 of t is an odd signal. Okay. Now this is very easy to verify. What? Because if I want to prove even signal, use a definition. That is, let's compute y1 of minus t. Okay. That is nothing but x of minus t plus x of minus t by 2, which is same as x of minus t plus x of t by 2. Now just rearrange terms. There's nothing but x of t. It means reorder the terms. X of t plus x of minus t by 2. But this is nothing but y1 of t, correct? This implies that y1 of minus t equal to y1 of t. That means what? Your y1 of t is an even signal. That because that's the definition of an even signal, right? Now similarly, let's take y2 of minus t. Okay. Now first let me write y2 of t first. Y2 of t, what was it written? X of t minus x of minus t by 2. So let me consider y2 of minus t. What is y2 of minus t? X of minus t minus x of minus t by 2 t minus x of t by 2. Take minus common, becomes x of t minus x of minus t by 2, or this is minus y2 of t. Is it clear?
Yes, sir.
So what does it mean? This means that y2 of t is an odd signal. Done. That's all. This is over. That is what I'm showing is if you given any signal x of t, I can write this as a sum of two signals where one is even, other is odd. And in particular, the even part of the signal x of t is given as x of t plus x of minus t by 2. And the odd component of the signal x of t is given by x of t minus x of minus t by 2. Okay, so this proves the result that any signal. This we did not assume x of t is one particular type of signal. This we proved for a general x of t signal. So that means any signal x of t can be written as a sum of even signal and an odd signal. Okay, that basically finishes this first question. If there are any doubts, you can ask me now. Okay, since there are no doubts, I'll go to the second question. Okay, now quickly let's recollect what we told about energy signal. So energy signal means what? Okay, we did not talk about energy signal. Sorry, we only talk about something called energy of a signal, not an energy signal. Okay, I'll tell you what an energy signal is. A signal is said to be an energy signal if the signal for which the energy is finite. The signal for which the energy is finite. Now, these types of signals are called energy signals. Okay, next, what is a power signal? A signal for which the power of the signal is finite. Okay, so these are the definition of what is an energy signal and what is a power signal. Now the question is as follows. Find the power of an energy signal. And second question is, find the energy of a power signal. Did you understand the question? Like what I'm saying is, first the question, what it says is, it's an energy signal and I want to find the power of it. Means what? The signal has finite energy. Then what is the power of such kind of signal? Similarly, if a signal has a finite power, what is the energy of such a signal? That is what this question is asking essentially. Okay. Now let's try to answer these, find the answer. Let's start for A part. That is, X of t is an energy signal. So what do you mean by energy signal? That is the Ex of t, that is an energy, which is defined as minus infinity to plus infinity mod of x of t square dt is equal to c, which is a finite number. Now for this x of t, we need to find the power, that is px of t we need to find. What is the definition of power of a signal? Limit t tends to infinity 1 by t integral minus t by 2 to plus t by 2 mod of x of t square dt. Now I can use this upper bound, that is I can bound this as is less than or equal to limit t tends to infinity 1 by t minus infinity to plus infinity mod of x of t square. Why? Why is this true? Because here I am only adding x of t square. It says, remember, mod of x of t square is a positive real number. Right? I'm adding positive real number only between minus t by 2 to plus t by 2. But on the right hand side, I'm adding from everywhere. So I'm only adding more number of terms in this integrand. If I add more positive numbers, this integrand can only become more larger. That's why this less than or equal to symbol. Everywhere it is same. Is it clear? Is this step clear? Can anyone confirm if this step is clear?
Clear, sir.
Yeah. Okay. And now what to do? Simple, right? This, I know this value. What is this value? What is that value? C, right? Because that's what is given in this Ex of t is defined as energy. That is equal to C. And this is exactly equal to energy. So this is limit t tends to infinity 1 by t times some finite number C. Now what is this answer? What is this? A finite number divided by capital T and t tending to infinity. What is this? Yes. Yes, it's 0. Right? It's 0 because limit of t tends to infinity 1 by t is what? 0. So it's a C is a positive, it's a some finite number because it's an energy signal. Okay, what does it mean? I proved that Px of t is less than or equal to 0. That is equation 1. Px of t is less than or equal to 0. That is equation 1. But power cannot be negative. Power is always a positive number. It's greater than or equal to 0. That is number equation 2. So from 1 and 2, what does it mean? P of x of t can only be equal to 0. So what does it mean? This implies that power of an energy signal is equal to 0. Okay, so power of energy signal is equal to 0. Now let's similarly try to solve the other question is energy of a power signal. Okay, so energy of a power signal. Let y of t be a power signal. Okay, what does it mean? Limit t tending to infinity 1 by t integral minus t by 2 to plus t by 2 mod x of t square dt is equal to some number t. It's a finite number. Okay, now this is same as, you can write this as limit t tends infinity minus t by 2 to plus t by 2 mod x of t square dt by limit t tends to infinity capital T equal to d. Now this is same as limit t tends to infinity integral minus t by 2 to plus t by
Sir,
2
sir,
mod x of t. Yeah.
should be y of t. No?
Oh yeah, you're right. It should be y of t. 1 minute. It is y. Y of t mod t square dt is equal to limit d times limit t tends infinity t. Now tell me what is this? This is basically equal implies minus infinity to plus infinity y of t mod square dt equal to d times limit t tends to infinity t. What is this? Now tell me what is the RHS value?
Infinity.
Yes, it's infinity. Now what is this? Ex of t, the energy of a signal. What does it mean? It means that I started with the assumption that my y of t was a power signal. That's because that's where the power was finite. But when I computed the energy of y of t, that is Ey of t, I'm sorry, not Ex of t, to compute Ey of t, Ey of t, sorry, it's Ey of t, it came out to be infinity. Okay, so what does it mean? This means that energy of power signal equal to infinity. So these are, we learned two properties. The power of an energy signal is equal to 0 and energy of a power signal equals infinity. Okay, so these are some very interesting properties of energy and power signals. In fact, there is a very interesting, why is a power signal and energy signal important? Important to know, right? In fact, it turns out that any periodic signal is a power signal. That is a cos 2 pi of ct. A cos signal or a sine signal or any periodic signal is said to be a power signal because you can show that. How do you show that it is? Or how do you show its power is it's a power signal? By using this property. If you compute the energy of the signal and if it turns out to be infinity, it will it's a power signal. You compute the energy of any periodic signal. You can show that the energy of a periodic signal is always equal to infinity. That's why any periodic signal is a power signal. Okay, that's where these properties are used. Okay, in fact, you can take this as a homework. You can take this as a homework. Your question 3. Using the trick that I told you, you can show the homework question. Show that any periodic signal is a power signal. Means what? Okay, you can show into any of the two ways. Show that the power is a finite number, or show that the energy is infinity. Whatever, whichever way you like, you can show. Okay, now let's move to the next question for today, after which we'll take a short break. Okay, simple. Now the question is simple. Find the energy and power of the signal x of t equal to e power minus 2 mod t. T ranges from minus infinity to plus infinity. Okay, so there is nothing very difficult about it. Just apply the definition of the energy signal, definition of power, sorry, definition of energy formula, and definition of power. Just compute the integral. That's all. Okay, let's do that. Solution. Let's first compute the energy. That is Ex of t is nothing but minus infinity to plus infinity mod of x of t square dt. This is same as minus infinity to plus infinity e power minus 2 mod t square dt, same as minus infinity to plus infinity e power minus 4 mod t dt. Now it's just you need to compute the integral value. Now we know that mod t takes two values, t if t is greater than 0 or minus t if t less than 0. Okay, so then this you can split the integral above it into two parts, that is from minus infinity to 0. Your mod t takes the value minus t, so it becomes e power minus 4 of minus t dt plus 0 to infinity e power minus 4 t dt. Okay, that is nothing but integral minus infinity to 0 e power 4 t dt plus integral 0 to infinity e power minus 4 t dt. Now it's just simple, something but e power 4t by 4 from minus infinity to 0 plus e power minus 4t by minus 4 from 0 to infinity. This is nothing but e power 4 is e power 4 e power 0 minus e power minus infinity by 4 and plus e power minus infinity minus e power 0 by minus 4. E power 0 is 1, e power minus infinity is 0, so it's 1 by 4 plus e power minus infinity is 0 minus 1 by minus 4, which is nothing but 1 by 4 plus 1 by 4 equal to 1 by 2. So energy is equal to half. Tell me, can anyone tell me whether is it an energy signal? Is it an energy signal or not?
Yes, sir.
Yes, it is an energy signal because half
Yes,
is
sir.
a finite number, right? So the energy of the signal is half, which is a finite number. So it is an energy signal. Implies that x of t is a energy signal. Now, now you should predict power I'm going to compute. What is the power of energy signal? 0. Okay, so we'll compute the power and show that it turns out it evaluates or it is equal to 0. We already know the answer, but we need to show. I mean, because we'll get practice to use the formula. Okay, so power is given by Px of t equals limit t tends to infinity 1 by t minus t by 2 to plus t by 2 mod x of t square dt. That is nothing but limits t tends to infinity 1 by t minus t by 2 to plus t by 2 e power minus 4 mod t dt. But now basically the limit is only over minus t by 2 to plus t by 2. So this is same as limit t tends to infinity 1 by t from minus t by 2 to 0, it is one value, which is namely e power 4t dt, plus 0 to t by 2, e power minus 4t dt. This is nothing but limit t tends to infinity 1 by t e power 4t by 4 from minus t by 2 to 0 plus e power minus 4t by minus 4 from 0 to t by 2. Now this is nothing but limit t tends to infinity 1 by t 1 minus e power minus 2t by 4 minus, I'm taking the minus 4 to this minus e power minus 2t minus 1 by 4. Now this is same as limit t tends to infinity 1 by t times 1 by 4 plus 1 by 4, which is 1 by 2 minus e power minus 2t minus e power minus 2t, which is nothing but, and 2 e power minus 2t, but by 4 is there, so I do something but minus e power minus 2t by 2t by 2. Is it correct? Okay, right? Yes, someone was about to tell. Okay, it's actually correct. Let's go ahead. Now let's compute the limit. Limit is nothing but limit t tends to infinity 1 by 2t minus limit t tends to infinity e power minus 2t by 2t. Okay, now this guy will go to 0, but this is what? T tends to infinity. This is a form what? E power minus infinity is 0, and it's like infinite 0 by infinity form. It's what is this? Indeterminate form. So what to do? Can anyone tell me what to do? How should I compute the limit? Yes,
We can differentiate.
correct. It's called, we'll use the so-called L'Hopital rule. Okay, so the limit t tends to infinity e power minus 2t by 2t is same as limit t tends to infinity minus 2 into e power minus 2t by 2, which is equal to 0. Okay, that means the power of the signal is 0 minus 0 equal to 0. Thus proved. Right, so the power of signal is equal to 0. This is not surprising. Why? I already knew that it is an energy signal from the previous, and I know that power of an energy signal is 0. And that's what we also got. So it's not something surprising. If the energy of a signal turns out to be a finite number, its power should necessarily go to 0. Similarly, the power is turning out to be a finite number, then its energy has to go to infinity. Okay. Now let's do, maybe we'll take some 15 minutes break. It's 7:08 now. We will meet back at 7:20. Maybe we can meet at 7:20. Is that okay?
Yes,
Okay.
sir.
Yeah, you all can remain in the call, but you can just take some relax and then come back at 7:20. But you can remain in the call.
Sir, I want to ask that can we get this page in our mail?
Sorry, I didn't understand your question.
Whatever you are teaching in this meeting, can we get its content in our email ID? Or
Yeah. Basically, I will upload the recording of the lecture and also the notes. Okay, I will share it with NPTEL. NPTEL will share it with you.
Yes, sir. Thank you. It will be very helpful for us, sir.
Yeah, definitely.
Hello.
Yeah, hello. Yeah, was there a question? Okay. Okay, let's resume. Question number 5. Let x of t equal to a sine 2 pi small t by capital T. Okay, that is, what does it mean? That is a frequency. Generally sinusoidal signal is 2 pi ft, right? Here f is nothing but 1 by t. That is frequency is equal to 1 by capital T. Let x of t be this a sine 2 pi small t by capital T. Question is, find the power of x of t. Very simple question, but the answer is a very interesting property which you can all remember easily, very easy. Okay, let's solve. Answer: p of x is nothing but limit t tends to infinity 1 by t from minus limit integral minus t by 2 to plus t by 2 mod x of t square dt, where t is the period of the signal. Okay, the same as limit t tends to infinity 1 by t minus t by 2 to plus t by 2 a square sine square 2 pi t by t dt. Now simple integration. Sine square theta is nothing but 1 minus cos 2 theta by 2. Therefore, your px of t is nothing but limit t tends to infinity 1 by capital T minus t by 2 to plus t by 2 a square by 2 into 1 minus cos 4 pi t by t dt. Nothing but limit t tends to infinity 1 by t into a square by 2 into integral minus t by 2 to plus t by 2 dt minus limit t tends to infinity 1 by capital T integral minus t by 2 to plus t by 2 cos 4 pi t by capital T dt. Now this is nothing but limit t tends to infinity 1 by t into a square by 2 into t by 2 minus of minus t by 2, which is equal to t. So t gets cancelled. So this limit is equal to a square by 2 only. Minus limit t tends to infinity. Oh, this is an a square by 2. Okay. T tends to infinity a square by 2t into sine 4 pi t by t by 4 pi by capital T from minus t by 2 to plus t by 2. This is nothing but a square by 2 minus limit t tends to infinity a square by 2t into t by 4 pi into sine 4 pi by t into t by 2 minus sine 4 pi t by capital T, sorry, 4 pi by capital T into minus t by 2. The same as a square by 2 minus limit t tends to infinity, tt cancel, a square by 8 pi into tt cancel, 2 4 cancel, sine 2 pi minus of minus sine 2 pi, that is plus sine 2 pi. But sine 2 pi and is equal to 0, right? So this entire term goes to 0. Therefore, our answer is a square by 2. Okay. In fact, so basically what it says is that if you take any sinusoidal signal, the power of the sinusoidal signal depends only on the amplitude. It doesn't depend on the frequency capital T. frequency is 1 by capital T. That is not there in the expression for power. Right. So in fact, I'm giving a general rule, very, very handy formula. You don't need to compute. You can directly, by looking at the signal, you can tell what is the power of that signal, as long as it is a sinusoidal signal. Okay. It's a property. Okay. Or maybe I'll say fact for, sorry. Okay. The power of any sinusoidal or cosinusoidal, whichever is it's cos or sine, doesn't matter, but it should be of the form sinusoidal, sinusoidal or co-sinusoidal signal does not depend on frequency or phase, because I told that sinusoidal has three components: amplitude, frequency, and phase. I'm saying that power does not depend on frequency or phase. It is always equal to power equal to amplitude square by 2. So it's a ready-made formula. So now tell me, I would like you to tell me question. Find the power of x of t equal to 8 sine 2 pi t by 24 capital T plus pi by 3. Can anyone tell me what is the power of this signal? Just by looking at the signal. Yes,
32.
32.
correct. How did you get 8 square by 2, which is 64 by 2 equal to 32? That's all. You can now, what you do, you go and apply the formula for power, integrate it, and prove that it's a homework, prove that it comes out to be 32. It doesn't depend on frequency or phase. Just look at the amplitude and tell what is the power. That's all. Amplitude square by 2. That's why I took this question, to say that these are some short, facts you can always, easy facts you can always remember. That will save you some time in computing the power. For any cosinusoidal signal or sinusoidal signal, power equals amplitude square by 2. Okay. Now the next question is question 6. Find the period of x of n. It's a discrete time signal. So I will not use, so x of t, right? I use a curly braces here, but I will now use a square bracket for a discrete time signal, just for difference, to tell the difference. But otherwise, all are same only. Find the period of the discrete time signal x of n equal to sine square pi by 2n, where n belongs to set of all integers. This means integers. Okay, it's a discrete time signal. So it's simple, right? All you need to do is find the capital T for which capital N. Here I'm denoting by N. So capital N for which x of n small n plus capital N equals x of small n. That's all. Just up to the definition. Okay. So answer, recall that x of n is periodic if x of n plus capital N equal to x of n. And in this case, n is said to be the period. And we need to find this. What is this? Capital N is said to be the period. We need to find capital N only. Okay. Now let's take the given question. X of n plus n is nothing but sine square of pi by 2 of n plus capital N, which is same as sine square of pi by 2n plus pi by 2n. Theta is nothing but 1 minus cos 2 theta by 2, which is same as 1 minus cos pi n plus pi capital N whole by 2. Therefore, in order for x of n to be periodic, we need cos of pi n plus pi capital N to be equal to cos of pi small n. Why? Because this will ensure that this guy will become equal to x of n back. Okay, so we just need to ensure cos of pi small n plus pi capital N equal to cos of pi small n. That's all. Okay. Because let me do because so if I call this equation 1, because with cos of pi n plus pi capital N equal to cos of pi n, the equation 1 becomes 1 minus cos of pi n by 2, which is same as equal to sine square pi of n, pi by 2n equal to x of n. Therefore, it is sufficient to find the capital N such that cos of pi n plus pi capital N equal to cos of pi small n. Okay, so now we'll go this cos of pi small n plus pi capital N equal to cos of pi n is the requirement. What does it mean? This means that your pi capital N should be an even multiple of 2 pi or integral multiple of 2 pi. Okay, where m can belongs to any integer z. This is the notation for set of all integers. Okay, or your let's say put m equal to 1. At m equal to 1, your n is equal to, or maybe let me simplify this. Cancel pi on both sides. So what does it give you? It gives n equal to 2m. This is the period. But what is the fundamental period? That is at m equal to 1. The first period. Fundamental period is at m equal to 1. That is n equal to 2. Therefore, n equal to 2 is the period of x of n. Okay. If there is any doubt, right? Please ask me right away. In fact, the period is not unique. I should be more precisely. N equal to is a fundamental period. N equal to 4, n equal to 6, everything is period because x of n is same as x of n plus 2, but same as x of n plus 4 and so on. So all of them are period. But more interestingly, fundamental period is what is important because everything else is a multiple of fundamental period. So fundamental period is what generally we are interested to calculate. Okay. If there are any doubt, please ask me right away. Okay. Since I didn't hear it from anyone, I hope everything is clear. Now let's compute. The next question is compute the value of the integral I equal to minus infinity to plus infinity e power t delta function, that is the unit, the impulse response, the impulse function delta of tau minus alpha by beta times t dt, where alpha, beta, and tau are some positive numbers. Okay. I just need to evaluate. So this problem is only to understand how to manipulate or how to compute, or how to basically work with formulas or integrals involving impulse functions or impulse signals. Simple, actually. All we need to do is just do some tricks in integrals, standard tricks, do variable substitution and do this and that, and then just simplify it. That's all. The first step, what I'm going to do is I'll define the dummy variable t dash. Define t dash as alpha by beta times the original variable t. This means your dt dash is equal to alpha by beta into dt, or dt equal to beta by alpha into dt dash. Okay. Now that means your I is now going to become minus infinity to alpha by beta, infinity into alpha by beta, and e power t. T is beta by alpha into t dash. Right. This also means t is equal to beta by alpha into t dash. So it becomes e power beta by alpha into delta of tau minus alpha by beta into t is nothing but t dash into dt dash into beta by alpha, because dt is dt dash into beta by alpha, tau is same as tau, alpha by beta into t is nothing but t dash, and e power t becomes e power beta by alpha and t dash. Now, how did I start up with this? Because see, my variable of integration is in terms of t, and there is already something multiplying t here. I just want to get of this. That's why I did a variable of substitution. Now you see the new integral. The variable of integral is t dash, and t dash is remaining as t dash only. Nothing multiplies it. That's why I got rid of this multiplier by changing the variable, by doing a variable substitution. This is nothing but, just now let me rewrite, minus infinity into alpha by beta is still minus infinity. This is also plus infinity. And beta by alpha, bring it out. This it's a constant, bring out of the integral. That's what I wrote it here. And this is e power beta by alpha into t dash into delta of tau minus t dash dt dash. Now, recall the property of the impulse function, impulse signal, that is delta of t is same as delta of minus t. Why? Because only at t equal to 0, it takes a non-zero value, right? And so at 0, 0 or minus 0 doesn't matter. So delta of 0 is same as delta of minus 0. This is the equation. Therefore, your integral origin integral is beta by into integral minus infinity to plus infinity e power beta by alpha t dash into delta of t dash minus tau. I just flipped the sign because delta of t same as delta of minus t in t dash. This is because of a, the equation a. Okay. Now, can anyone tell me? Okay, this is same as beta by alpha. Can anyone tell me what is this answer? Yes.
Sir, hello.
Yeah. Tell me.
Sir, can you hear me?
Yeah. I can hear you. Yes.
Sir, we can use the property of integral minus infinity to infinity x of t delta of t minus t dash equals to x of t dash.
Correct. So exactly. So you see here the variable of integration is t dash. Okay, and tau is like your t naught. Okay, if you remember the formula, what did we say? We say integral x of t into delta of t minus naught is same as x of t naught. You remember this expression? The very beginning of today's session, we saw this. So by going by this expression, that is by using the shifting property, this is same as either b into yes, b by beta by alpha into. Do you agree? Do you agree? Anyone? Is it okay? What did I do? I just use shifting property. Let me tell you. That is integral minus infinity to plus infinity x of t dash. Now I'll just write in terms of t dash into delta of t dash minus tau into dt dash is same as x of tau. Okay, so think of your x of t dash as e power b by beta by alpha t dash. Now is this okay? Because it's nothing but x of tau, that is e power beta by alpha into tau. Is it okay?
Yes, sir.
Yeah. So that's all. This is the answer. So the integral is nothing but I equal to beta by alpha into e power beta by alpha into tau. So we have just used the properties of impulse function, namely that it's an even function and the shifting property of an impulse function. Okay, related to impulse signal, I'll ask you another nice question. This is question 8. I'm going to ask a plot, okay? Plot. That is simple, right? Something like it is a for every t not equal to 0, it is 0, and at t equal to 0, it is going to infinity. So for that, we say we put a vertical bar and say an upper arrow, saying that it goes on and on. It's a very large number. This is how we represent an impulse function. We put an arrow mark on top, saying that it just keeps on going up. Now, this is not something difficult. What I'm going to ask is as follows. Plot delta of cos 2 pi t with respect to, versus t. Do you understand what I'm doing? This is nothing but composition of function. That is, if let's say you define f of t as delta of t and g of t as cos 2 pi t. I'm essentially asking the signal x of t given by f of g of t. I mean composition of two signals. So I'm asking you to plot the signal which is obtained by composition of two signals, where the first signal is basically you first take the cos 2 pi ft and then you composite that with the impulse signal. Okay, so this is an example of composition of two signals. Now I'm asking you to plot delta of cos 2 pi t. Now how to do this? Just use the definition of delta. What does delta function do? Delta function will assume some non-zero value only when the argument of delta is equal to 0. Okay, so for the first point is check for all values of t such that cos 2 pi t equal to 0. Why? Because only delta of 0 is non-zero. Delta of any other number is equal to 0. Therefore, you first find all t such that cos 2 pi t becomes 0. Whenever that becomes 0, I'll have a peak in the delta, right? So essentially, find all those t such that cos 2 pi t equal to 0. Now tell me, if cos 2 pi t equal to 0 implies your 2 pi t should be equal to what should be your 2 pi t? It should be an integral multiple of pi by, correct? Pi by 2, 3 pi by 2, or pi by 2. Okay. Yeah, maybe 2 pi t should be equal to pi by 2, n pi by 2, right? Where n belongs to range of set of all integers. Or is it okay? 2n plus 1 pi by 2, right? Not just n pi by 2, because it should be odd multiple of pi by 2. Because at cos pi, it is taking the value -1. It is not 0. It should take odd multiples of pi by 2. Only then it is cos of odd multiples of pi by 2 is equal to 0. Okay, is it okay?
Yes, sir. Yes, sir.
Yeah, that means what is the value of t? T is equal to 2n plus 1 into 1 by 4, where n ranges belong to all integers. That is all odd multiples of 1 by 4 is what you need to take. That means at all those t equal to odd multiples of 1 by 4, your cos 2 pi t will become 0, or your delta of cos 2 pi t will be equal to non-zero value. Therefore, this is how your plot of delta of cos 2 pi t will look like. Draw the t-axis. This is at t equal to 0. At t equal to 0, will you have a delta function? No, right? Because at t equal to 0, cos 2 pi t is equal to 1. Delta of 1 is 0. Delta of 1 is not non-zero. Therefore, you will not have at t equal to 0. But you will have at odd multiples of 1 by 4. That is 1 by 4. You will have one peak. 3 by 4, you'll have one peak. 5 by 4, you'll have another peak. And in the left hand side, similarly, you can have minus 1 by 4, minus 3 by 4, and so on. It will keep on going. Okay.
Sir,
So
impulse
this is the
function is
plot.
only. Sir,
Sorry. Yeah.
impulse function is only 1 at the 0 time of 0. So how these times are getting high value?
Correct. Impulse is 0 when you should understand that the argument of impulse, if it is 0, then only this delta will take maximum. If the argument is not 0, then delta will take 0. Do you agree with that? See,
Sir,
delta of x will be equal to 1, or sorry, it will not be equal to, okay, maybe I will say, okay, delta of x is equal to 0 if x is not equal to 0. Do you agree with this? Whenever x, the argument of delta function is not 0, only then delta, the argument is not 0, only then at those points delta is equal to 0. Do you agree with that?
yes, sir, yes.
Now, see, your t is not coming as argument. T is coming in one more function, cos 2 pi t. So you should look at all, I'm asking you to plot versus t. So you should look at all those t such that cos 2 pi t is 0. Only at those points your delta function will have 1. Do you agree?
Sir,
Is it
delta of
okay?
x is 0. Delta of x will be 0 if x is not
Correct.
equal to.
Correct. Now treat this is basically your x, right?
Yes,
You
sir.
need to, now
Yes,
I'm
sir.
asking you to plot with respect to t, not with respect to x. That means I need to
Yes, sir.
find all those values of t for which x is equal to 0. Only there I will have these peaks.
Yes, sir. Yes, sir. Got it. Got it.
That's what I'm doing. So I need to find all these guys where these guys become 0, or find all the values of t such that cos 2 pi t is equal to 0. And it turns out that all this odd multiples of 1 by 4 cos 2 pi t will go to 0, or delta of 0 will be not equal to 0. That is, it will have these arrow marks. That's what I drew it here.
Yes, sir. Thank you. Thank you, sir.
Yeah. Okay. We will solve maybe one more question and then maybe we'll stop for today. Question is as follows. We'll go to the next page. Question 9. Okay. Discrete time unit step signal is given as follows. U of n equal to 1 if n equal to 0, 1, 2, and so on. 0 if n equal to minus 1, minus 2, minus 3, and so on. That is basically what I'm saying is your discrete unit step signal is as follows. At 0, 1, 2, 3, everywhere it is basically 1, and so on. This is at 1. This is basically like u of n. And everywhere in negative axis of n, minus 1, minus 2, it is all 0. Okay, basically the unit step function in continuous time signal, that is, if you sample that, you obtain discrete time unit time signal, that unit step signal. That is what I'm showing here. This is basically discrete time unit step signal. Another signal is basically discrete time impulse signal. Discrete time impulse signal is given as delta of n equal to 1 if n is equal to 0, 0 if n not equal to 0. That is, if I plot this, essentially you put all n, only at n equal to 0, you will have some non-zero value equal to 1. Everywhere else, it is 0. Okay, this is basically called discrete time impulse signal. Now the question is as follows. Question A. Express the discrete time impulse signal in terms of the discrete time step signal. B. Express the discrete time unit step signal in terms of the discrete time impulse signal. These are the two questions. That is, I want to write delta of n in terms of u of n, and I want to write u of n in terms of delta of n. That is the question to us. Okay, let's do this. So very simple again. Let's do this. As I do, you will see how simple it is. First is A. That is, I want to express delta of n in terms of u of n. Now, what is u of n? It is of this form. N at n equal to 0, I will have 1. At n equal to 1, I will have 1. N equal to 2, I will have 1, and so on. But at n equal to minus 1, I have 0. N equal to minus 2, 0, and so on. Now, consider u of n minus 1. Now, the question, someone asked me, what is the delayed version of the signal in the starting of the class, right? Now, this is the delayed version. That is, now, how will u of n minus 1 look like? Remember, how do you define u of n? Whenever the argument is greater than, whenever the argument n is greater than or equal to 0, you get a 1. Correct? Similarly, for u of n minus 1, whenever n minus 1 is greater than or equal to 0, this u of n minus 1 is equal to 1. Correct? Therefore, u of n minus 1 equal to 1 if n minus 1 is greater than or equal to 0, that is, or equal to 1 if n is greater than or equal to 1. Do you agree? That means u of n minus 1, the plot of u of n minus 1 is as follows. Instead of starting at n equal to 0, I will start at n equal to 1. From 1 equal to 1, I will have all ones. And so on. But for n equal to 0, you will have 0. Is it okay? Is it okay? Can anyone confirm?
Yes, sir.
Yes, sir. Yes, sir.
Yeah. Now can anyone tell me, just by look, now let me just put that figure. Delta, recall, delta of n is nothing but, everywhere it is 0, except at n equal to 0, it is 1. Now, can anyone look at these three figures, u of n minus 1, and delta of n? Can you see these three figures and tell me, how can I obtain delta of n using u of n and u of n minus 1?
U of n minus m is greater than or equal to 0 if m is greater than or equal to 1.
That's correct.
When-
But my question is, can I do some operations on these two signals so that I will get delta of n? That's my question.
U of n minus u of n minus 1.
Exactly. If I subtract these two signals, right, this one here will cancel with this one. This one here will cancel with this one. Everywhere it will cancel. But this one at n equal to 0, there is no 1 in a u of n minus 1 to cancel out. So 1 minus 0 will be equal to 1. So at n equal to 0 alone, you will have 1 here. That's what is delta of n. Okay. Therefore, u of n minus u of n minus 1 is nothing but, I will do this. Maybe it will be very clear to you. At minus 2, it's 0. At minus 1, it's 0. At 0, it is 1. At 1, it's 1. And 2, it's 1. This is u of n. Minus 0, it is 0. 1, it is 1. 2, it's 1. 3, it is 1, and so on. Minus 1, minus 2, 0, 0. When you subtract these two, what you will get is, at equal to 0, you'll get a 1. Everywhere it is 0. Okay, which is nothing but delta of n. Therefore, delta of n, you can write it as u of n minus u of n minus 1. That is, if you subtract the actual unit step response and the delayed version of unit step response, you will get a unit impulse response. That is unit impulse signal. Okay, so we have expressed the impulse signal in terms of your discrete time step signal. This is the correct answer. Now, similarly, let us express the other way. That is, you need to use impulse signals to obtain U of n. Okay, now I will give you the clue. Clue is as follows. Delta of, okay, what is, okay, here is a follow. Delta of n is what? At n equal to 0, you have 1. What is delta of n minus 1? Whenever the argument goes 0, I will have a peak. When will the argument go 0? N equal to 1. Therefore, at n equal to 1, I have a 1. Similarly, delta of n minus 2 is what? At n equal to 2, I will have a 1. Similarly, a delta of n minus some k is nothing but at n equal to k, I will have a 1. Now, can anyone tell me how to obtain delta u of n from these deltas?
Delta n plus delta n minus 1 plus delta n minus 2, so on to delta n minus k.
And so on. K will keep on going on. Exactly. So you just add all of them. All of them you add. Therefore, your u of n is nothing but summation over k equal to 0 to infinity delta of n minus k. Is it okay?
Yes, sir.
Yeah. Okay. So actually I had one more question, but that will take time. Maybe this is the right time to stop. If there are any questions, we can take. Otherwise, we can stop for today and continue next week.
Okay, sir. Thank you.
Yeah. Okay.
So when it will
Okay,
be
then
available on the site?
Sorry.
When it will be available on NPTEL site, your this lecture session?
They will let you know. I'm not sure. I will share it with them, and they will let you know when it will be available.
Yeah, you can't share directly with us.
No, I don't know actually when it will be available. I don't know.
No, I was asking
Maybe
that
just
you
give
can,
maybe
can you
give
share
1 or 2 days. Sorry.
can you share it directly with us?
Oh, I don't have access to any of your contacts because all of you have been added to NPTEL course. So I don't have any permission to share directly with you. I only have the permission to share with NPTEL, and they will share it with you. Maybe it should happen within 1 day, not more than that.
Okay, sir. Okay.
Sir, it was the first live class, I think.
Yes, today is the first live class. Um, I think in a day you should be able to receive the link for all the notes. Okay.
Sir, which book we should follow for this type of questions?
Okay. So I think Professor had mentioned right on his course page. There are
Yes.
several. So signals and systems is a very basic course in this for across many engineering domains. Um, for example, very standard books like Oppenheim, Signals and Systems, or Simon Haykin's Signals and Systems are all very good books. They're all very standard books. Think whatever material professor suggested are all very standard and they are mostly used everywhere. So you can refer those books.
Okay, thank you, sir. Thank you.
Yeah.